Hello everyone, welcome to Lambda Days 2021. I'm Taine Zhao. I'm from the University of Tsukuba, Japan. And today I'm very honored to be part of this program. And today we are talking about making JIT compilers for dynamic programming languages in an easy approach. So firstly, let us get some knowledge about the background. Now is a runtime compiler that tries to collect information at runtime and use this information to generate more optimized code at runtime as well. So there are still some issues to implement a JIT compiler. For the non-technical part, the human resources and the money that can be invested in are always limited. And when it comes to the technical part, we have to consider the compatibility to the existing ecosystem, and we have to consider the complexity of the project and the time spent. I think that if your JIT compiler is too complex, you have to maintain it in a very hard way. I mean, the human resources are very limited. It's a bad practice. And the time, if you spend too long time to implement a JIT compiler, it may not be very easy for you to sync up with new language features and new patches because every program language is in active development. So it will be hard for you to do it. And due to above issues, the progress of making JIT compilers for dynamic programming languages in many dynamic programming languages is quite limited, especially in C Python. And we observe this and we try to make a new approach, a working approach, and apply it to Python. We implement our core compiler within 1,000 lines. And we do not introduce invasive changes to the language implementation. What does this mean? C Python is written in C, but we do not concern about the C part. We just implement the JIT compiler as a regular C pure Python third-party library. And we also keep very good compatibility to the existing ecosystem. We even encourage the use of C extensions, and this is quite different from other Python's JIT compiler attempts. And we also consider the extensibility. What do I mean by extensibility? I mean, if you want to add some optimization to the JIT compiler, usually within our framework, you do not need to modify code from the compiler side. Instead, you just write something like a plugin that implements analysis, and this will be automatically applied to the compiler, and then you get the optimization. That's all. So our approach starts from the call size specialization. A call size specialization is very common in the scope of optimizing dynamic programs. And it takes such a form. We have a callable f and several arguments, arg1 to argn. We use callable here because many dynamic programming languages, they are object-oriented programming languages. Everything is an object, and some object is callable. By partly knowing the information of the callable f and its arguments arg1 to argn, we may be able to firstly choose the appropriate implementation of f. This will be faster, and then we may be able to eliminate runtime type checks. And thirdly, we may be able to infer the representation of the return. Usually, we just infer the return types, but sometimes we may also be able to infer that the return value must be something. This can be done by our JIT compiler at analysis time. And we distinguish the call size specialization into two categories. The first is the immediately invoked specialization. We call it IIS. The IIS is a specialization that is performed on the callable exactly when executing the code. As you can see in the above code, when we want to call the function upon 3, we firstly trigger the JIT compiler, we compile it, we got the specialized function. And also, by doing this, we have to pass some runtime information like the argument types. And then we got the function and we call it. So this is specialized and then immediately get invoked. So we call it IIS. IIS triggers the compilation, so it is very slow, it's time consuming. So if you want to really make a program run faster, you have to consider another kind of specialization. We call it pre-call specialization. PCS, pre-call specialization. A PCS happens inside an IIS. And suppose here, when you are doing an IIS, you call this function, and you pass some runtime information to the compiler, and then you can propagate the information. And here you know, oh, XS is at least, and you are accessing the method append, and then you will be able to optimize this statement if you have some registered rule for this. What do I mean by the register rule? You define some specialization rule matching the case, like access is a list and the method is append, and there is one argument, and you define such a rule, and then you can apply it. We simplify our above code, and we just focus on the most interesting part. So as you can see, there is an IIS, and we pass the runtime information in, and we got a value store. We know XS here is a list. We know the type is list, and the type of X is top. This means that we don't have any exception to the variable X, and we will be able to specialize this function by given such a specialization rule. So XS is a list, and the case is that the method is append, and there is only one argument. And then you can specialize it to an intrinsic function call. The intrinsic function C is append. It's just like a C function, and it implements the behavior of list append. So it's faster, right? And it's a specialized implementation that you can avoid type checking the arguments, and you eliminate the dynamic method lookup. And you can it also helps to guarantee the return. Define some rule for, and it will be used when analyzing the code. So yeah, it's very simple. So we come to another case that if you have got some idea about our compiler, you may find that we come to another example. First thing, we didn't give any exception. We define a data structure. We call it node, and it has two fields. The first field is next. Next can point to another node or empty or that iterates over the whole integer linked list and try to sum up all the value fields. And running this pure Python code a million times costs nearly 9 seconds. It's very slow, right? The performance is very poor because, because at 9, you see here, Python just used generic addition here. But we can know here, we know in the call set, we will be able to know this is just, as a coder, right? As a coder, we know this is integer, this is integer. So we can use integer addition here. So we can still try to decompile it without given any exceptions. And here, we will still produce a performance gain of 40%. This is because we just eliminate the interpretive overhead. But the compiler will complain about that it will finally converge to some states that every variable is analyzed to have a top type. This means that we lose exceptions for every variable. And then at the line 9, we have to admit that we cannot infer the type, and this operation must be a generic addition instead of integer addition. So since we'll change if you give some exceptions to the compiler, you tell the compiler that we can tell the compiler that the next field must be either a node or a unit, and the field value must be an integer. We just tell the compiler it, and then we trigger the compilation, and the compiler will tell us it can infer every variable's types at every program point, and it will be finally we will find that at line 13 we will be able to know at 13, we will be able to know a is an integer and n is a load, so n.var must be an integer. So at here, we always can specialize it to an integer addition. And this will produce a performance gain of more than 140%. And actually, that's all. That's so simple, and you can use this strategy to optimize Python programs very large factor. And our G-compiler is not only a G-compiler. We can also use it to do something interesting. Let's see an example that you have a Fibonacci function. Firstly, you just G-compile it, and at this version, you just G-compile the operator to the integer ones. I mean, the comparison, you specialize it to integer comparison, and you specialize this to integer minus, integer plus. But still, there are chances for you to compute some things like a ladder system, just like constant explorer in C++, right? And we define the underscore. We use such a notation. Underscore function is a variant of function that tries computation at the lattice time. And at here, we define the underscore. How we define the underscore Fibonacci function? It's defined by using the underscore operators, like less than, equal, and minus, and plus. And we call this underscore Fibonacci function. In the first call site, we will be able to know x is can be known at a lattice time, because the compiler can infer this, and this is and here the value representation of x will be known. So we will be able to compute things at a lattice time. But in the second call, this is actually specialized when you trigger the IIS for main function. So you pass information, the y is an integer, but you don't have the value representation of the of argument y. So you have to say, oh, I fail at compute things at a lattice time. So I just do the ordinary G-compile strategy, and it will fairly produce the same code just as the first Fibonacci does. And as you can see, the performance gap, there's a performance gap. In the first naive version, you just got a 600% speed up. But in the second version, it's a much larger scale. And so you may be interested in how to define the underscore operators. Yeah, because we haven't mentioned it before. So we just give an example of how to define the specialization rule for underscore plus. Underscore plus, you first need to define such a Python object. It just implements the ordinary generic addition behavior. But now you just register special rule, a special specialization rule for this underscore plus operator. Yeah, it's also a Python object. Yeah, it's also a Python object. You register it, and you say, if I call it, I will try to check if the two operands are static. If they are static, I try to compute it at a lattice time. So we don't explain much about this course. I just want to let you know that we can register a specialization rule in pure Python, and we can do this. And this is what we call extensible. And we also have done several benchmarks, and the results looks quite positive to actually to me. But there are still cases that we cannot optimize, and there are still some. Yeah, so we come to the final slide of this presentation, and our optimizer, G-compiler, can also optimize encourage the functional programming, because we can optimize immutable data and smaller functions. So that's all of my today's talk. Thank you everyone for listening to my talk. If you have any questions, please ask in the QA section. So, Peter?
So thank you very much for your presentation.
Could you hear me?
From everyone. So apparently they liked it.
Yeah.
If someone has a question, please enter it in the feed or in the Q&A section, or you can raise your hand and I can give you the floor. If not, I have a question. I'll start with that. You do computations at the analysis time in order to achieve these nice speed ups. do you assume that everything terminates, or is there something special for termination?
Yes, that's the point. If you want to, by default, we didn't do partial validation. And if you want to do something, you want to try compute something at a later system, you have to maintain the termination condition yourself. Yeah, so that's So if you want to do this, you have to guarantee it yourself. Yeah.
So it's the user's responsibility to ensure
user's responsibility. Yeah, that's it.
Okay.
Yeah.
Like usual in programming.
Yeah. So, any other question?
Okay, there was a remark in the feed, and there's a question in the Q&A. The question is, I don't see a raised hand, so I'll read it out to you. Can you describe the functional points when lots of Python is so imperative?
I mean, the functional point here is that if you write functional code, it will be easier for us to optimize it. But you can still try to write an ordinary imperative code, and in this case, the optimizer may perform worse than optimizing the functional code. Yeah, this is intentional. Could you maybe we invite Varun to ask me?
Only if he raises his hand, and he didn't.
Okay.
So I can't do that. Okay. So thank you for this answer. But there's no assumption in your system that everything must be functional. Just Python code, and if it happens to be functional, you can do better things, and otherwise you just give the best attempt. Is that correct?
Sorry, I didn't get you. Could you please repeat again?
Oh, so if the Python code happens to be functional, then you can do better optimizations, but that's not a requirement that you can only handle functional Python code. So thanks for the clarification.
Okay.
More questions?
Yeah.
If not, then I would like to thank you again, and then we will move to the next session. We have a couple of minutes to switch sessions. So
Peter has asked a question.
Oh, there's another question in the Q&A. Let's see that.
Yeah, I haven't. Yeah, I just compare to my counterparts, like other existing attempts to see Python, but I didn't. I haven't heard about FPLs.
FPLs are just functional programming languages.
Oh, sorry. So JIT approaches in FPL. I'm not sure what you mean by this. So you mean my implementation is written in FPL, or what do you mean? I'm not sure what Peter mean by this.
I guess he means other approaches to just-in-time compilation in other functional programming languages. Do you know if there's some other work, or isn't there any work?
Yeah, I haven't studied the JIT approaches for functional programming. I just usually focus on the dynamic programming languages. Yeah, but I used to write the JIT compiler by using the FPLs. Yeah. Hi, Peter.
Okay. Hi, Peter is there, so he can.
Hi. Yeah, sorry for very briefly typing in the question. I wanted to quickly put in the question before we stop. So my question is basically, have you compared your work with dynamically typed functional programming languages that might happen to use just-in-time compiler? Actually, I don't know of any of those languages. I was just curious about this.
You mean my comparison to against which? Against I'm not sure. You mean?
Yeah, let me rephrase. So, do you know of functional programming languages that are also dynamically?
You mean? I got you. You mean something like Erlang or something like that?
Yeah, I was thinking more like Racket or Scheme.
Yeah, I haven't compared with Zim. Yeah, that's. I used to write some some article, but I haven't give some serious research about Zim. Yeah, so yeah.
I don't know if there's somebody in the audience who knows if there are JIT approaches in functional languages. Well, anyway, thank you for your presentation.
Yeah.
Taine Erlang has a just-in-time compilation.
Yeah.
Which will be released in the next version, so it's also not really currently available yet, but it will be soon.